All right, good morning, everyone. Welcome to this session. My name is Ankit Asthana, and I am a program manager on the .NET team. And with me, I have
Gal Oshri. I'm a PM on the AI platform team.
And what we're going to be talking about today is machine learning in .NET with ML.NET. So let me just ask you a very quick question here. How many folks in the room are comfortable or are experienced with machine learning? Can we have like a raise of hands there? OK, and how many folks are essentially getting started with ML? Is there a lot of folks getting started with ML? Perfect. So as you know, as a .NET developer, as you know that .NET is a great tech stack for building a wide variety of applications. You can build web apps with ASP.NET. You can build mobile apps with Xamarin. And what we're focusing on in this session is really how we're making .NET great for machine learning. So for those in the room who are just getting started with machine learning, we have a couple of slides just to give you a little bit of context on what machine learning is really all about and how to think about this problem. Gal, do you mind?
Sure. So one way to think about machine learning is that it allows you to program the unprogrammable. So if I asked you to write a function that takes an image as an input and outputs, is there a face in the image, it's not really clear how you would start that. Or if I asked you to write a function that takes the description of a shirt and outputs the price of that shirt, you might look for some keywords that would give you a hint, but that wouldn't necessarily work really well, and it wouldn't scale to all the items in your catalog. So even though we don't know how to write this function, we do have many examples of these inputs and outputs. We have many images that we can take and label them as having a face or no face in the image. And machine learning lets us take that data and create a model out of it. Now, one way to think about that model is that it's just a function that does that input to output that we're looking for and detects a face in the image. Now, there are many tasks in machine learning. Just to give a few examples, classification is extremely common, and that is when you're trying to decide whether something is A or B. When we're looking at whether there's a face or no face in the image, that's a classification problem. Regression is when we're asking how much or how many. If we're trying to predict the temperature tomorrow or the price of a shirt based on a description, that's a regression problem. Clustering is when we're thinking about how is the data organized? What are the groups in the data? If I have a collection of news articles and I want to detect what are the different topics or groups within them, that's a clustering problem. So Ankit will now show us one example of how the .NET team uses ML.NET.
That's right. So I'm just going to switch over here. So here's an example, like of how we're going to use how we're using machine learning in the .NET team. So here you have the .NET Core Effects repo. This is where where our source code is for the .NET Core Foundation libraries. You can see that here. And if I go into the issues sections, you'll see a variety of issues here that folks have filed. Each of these issues has essentially a label tag to it, the ones that have been triaged so far. So what we're going to show you here is let's go ahead and create a new issue. I'm just going to use my cheat sheet here and just add the title for this issue as client WebSocket does not provide upgrade request error details. And I'm going to add a description to this issue. And what I'm going to do next is I'm going to go ahead and submit this issue. And once this issue is actually open, we're going to use a ML.NET model to be able to classify the label on this issue automatically. So let me go and submit this issue. You can see that this issue is now open, and there's no labels on it yet. I'm quickly going to hover over here, and I'm going to run this little app here. And all this app is doing, it's taking a ML.NET model, and it's pulling down the GitHub issues using the GitHub APIs. And then it's labeling these issues using a classification model that we've built. So you can see here, as in the diags here, that it basically says that issue 32480 was labeled. And if I go back to my GitHub repo here, where I just opened the issue, you'll see that this issue now has a label, which is area system net. And you can see this issue tag, this label was just added now. So here's kind of like an example of how, as a .NET team or in .NET as we're approaching machine learning, here's one of the cases where we've applied ML, and we're using a model built in ML.NET at scale. As we go through later in the talk, we will get into how we build this model. So before we go further, I just want to give you a little bit of background about what ML.NET is. So as you're starting with ML or machine learning, one way to get started with ML is to use pre-trained ML. And on the Microsoft stack, Azure Cognitive Services provides a great way to get started with pre-trained ML. So in this case, the example you're seeing here is of a sentiment analysis issue being of sentiment analysis. What we are filing in here is a product review for a vacuum cleaner. So the product review says this is a great vacuum cleaner. And I give this product review to the text analytics API, which is going to return back what you probably expect, a positive sentiment for this particular product. Now, what happens if I slightly change this example to be about this vacuum cleaner sucks so much dirt? So what's going to happen now is that if I go ahead and again use the pre-trained ML model, the sentiment now drops to 9%, only being 9% positive. It's fairly negative at this point, right? So what I'm trying to highlight here is some of the limitations with pre-trained ML. Pre-trained ML or pre-trained machine learning models is a great way to get started, and it will work well for a specific set of scenarios. But for some other scenarios, what you need to be able to do is you need to be able to build your own models. And the steps required to build your own models are essentially starting with your data. So in the example that I just showed you, in the vacuum cleaner example, you want to start with your own domain data set and train and build your model with that data set and then run and deploy that at production at scale. And when we talk about ML.NET, ML.NET is really a framework for building your own custom models entirely in .NET. Because it's a framework, it has a set of APIs. So it has developer-friendly APIs for training and consumption. And by that, we really mean is that we took a look around in some of the other machine learning frameworks like TensorFlow, scikit-learn, XGBoost, and so on. And what we've tried to do is we've tried to extract the best behaviors from those frameworks and also look at some other frameworks in .NET like ASP.NET and Entity Framework and come up with these APIs which to you as a .NET developer will feel natural. The other thing this framework comes with is out-of-the-box transforms. So as I kind of like talked about in the last slide, when you're doing machine learning, one of the tasks that you spend a lot of time on is essentially data prep or transforming your data or feature engineering. And so ML.NET comes with these transforms, which are very useful in massaging your data. It has transforms like text transforms or categorical transforms. It also comes with some of the classical machine learning algorithms, which are going to be able to do tasks like the classification example that I just showed you with GitHub, or clustering that Gal just talked about. And then lastly, ML.NET is extensible, which means that we can extend this for other scenarios. So for example, we've just, in ML.NET 0.5, we extended ML.NET to add deep learning support with TensorFlow. TensorFlow is the leading library for machine learning, deep learning, essentially. And the other things we've also extended this to is Onyx. And these are all the things we're going to get into today. The next set is essentially a lot of demos. But I just want to give you a little bit of background on what ML.NET is about. And while ML.NET is something we launched at Builds, it's about only 5 months old externally, it's heavily used within Microsoft. It's been used for a decade. A lot of these products in Microsoft are written in .NET. And ML.NET is really powering these products, right? So Bing Ads uses this for click ad predictions. Excel uses this for recommended charts. Windows uses it for device guard. Windows Hello uses ML.NET. So every time you're signing into your Windows desktop machine or laptop machine, there's a model being used from ML.NET. So what we're trying to get at here is that even though ML.NET is externally available only now, the core piece of ML.NET is extremely battle-hardened as a result of being used in all these products. The last thing I also want to point out is Azure Streaming Analytics is another service that we have. It does real-time analytics. And they've just started using the open source version of ML.NET for using as a part of their anomaly detection built-in model. So just to summarize this slide here, ML.NET is for making machine learning accessible to all .NET developers. It's for building your own models. It's heavily used within Microsoft, so it's proven at scale. It's open source, it's cross-platform. And again, what we're doing with ML.NET is we're trying to focus on developer scenarios that you've heard of, scenarios that you probably have, and we want to be able to empower you being able to be successful in building those scenarios. You can check out our GitHub repo there, where all the source code for the machine learning ML.NET is. The publicly version available right now is ML.NET 0.5. And just to highlight some of the scenarios that we're going to demo next, here are all the things that are possible with ML.NET today as is, right? So if you go to the Microsoft, if you go and grab the Microsoft.ml NuGet package and check out our repo, you can actually build custom models entirely in .NET for sentiment analysis, for GitHub issue classification, for image classification. If you want to build a forecasting model, you can build that with ML.NET. You can do predictive maintenance. You can do recommendations. So if you have an ASP.NET web app, you can actually add product recommendations to it. And these are all the things that you can do today with ML.NET already. And some of the things that are not mentioned on this slide are available at our samples repo. You can check that out. So we have examples there of end-to-end and getting started samples that will show you how these scenarios are built. So with that, we want to go ahead and start showing you some of these apps that we're going to build from scratch, and we're going to show you how we're building this. So we're going to start with the first one here, which is sentiment analysis. Does that sound good? Perfect. OK. Yeah.
Thank you. So let's start with a simpler example than GitHub. This is sentiment analysis. And the data set that we'll use is the Wikipedia detox data set. So this is a collection of comments and a label that says, is the comment toxic? Is it a personal attack on someone? So you can see a few examples here. If you're saying to someone, you're so rude, maybe that's a personal attack. But if you're saying, oh, thank you, that's not toxic. Now, in machine learning terminology, the input to that machine learning model, the function that we discussed earlier, is called features. This is the information available to us when we need to make a prediction. So what we're going to do here is train a model that can take in a new comment when it comes in and predict, is this a personal attack? Do we need to potentially investigate this comment or block it for now? So features is the input. The label is the output. It is the thing that we're trying to predict. With this information, features and label, we can train a model to give us that function that we want. So this is an example of a classification problem, because we're trying to determine whether the comment is positive or negative. Is it toxic or not toxic? Now, just giving a high-level overview of the machine learning workflow, we're going to first collect the data and load it. And then we're going to extract features from it. We're going to transform the data into a format that's usable by the machine learning model. This might mean converting all the text that we have into numbers that the learning algorithm can understand. Once we have everything in a numeric format, we can actually train the model. And then we want to evaluate it. We want to understand, is this model actually good? When a new comment comes in, are we actually going to predict whether it's a personal attack correctly or not? If we're happy with the performance of the model, we can then actually start consuming it in our app. So this could be a completely separate app where we just took the model that we created and started using it to make predictions. So let's talk about a few important concepts that we'll then cover in the code. So don't worry if they sound a bit complicated. But the first one, data, is exactly what you think it is. It's just the data that we have. It is like a SQL view. It's lazily evaluated, heterogeneous, and has a schema. Next, we have a transformer. It is something that takes data, does some work with it, and then outputs new data. So we talked about needing to transform the data into a format that's usable by the learning algorithm. So an example of that is a text featurizer. It takes the text in the comment and then converts it to a numeric feature that represents, to some extent, the meaning or the words in that text. The approach that we follow here, if you're familiar with it, is n-gram extraction, where we're looking at the sequences of words and characters and mapping them to numbers that the algorithm can then use. Now, how do we get these transformers? Estimators are the things that take in data and do some learning on it to produce that transformer. So the thing that we're actually trying to come up with, the model, can actually be trained using an estimator. We're going to provide it the comment and the label, whether it's toxic or not, and it will create a transformer, in this case the model, that takes the input and gives us the output. And then a very simple, just convenient wrapper around that model concept that takes in many rows of data and gives us the many rows of predictions is just the prediction function, which takes a single instance of input and gives us a single instance of the output. Because when we deploy the model, we just want to optimize a few things and deal with issues or comments as they come in one at a time. So the example here is one comment comes in, and we just get a predicted label out of it. So now Ankit will show how we actually do that in code using ML.NET.
Right, so hopefully folks at the back can also see the code here. Just a slight show of hands there. OK, perfect. So here I have Visual Studio. And what I want to show you first is how do you grab the ML.NET NuGet, right? So when you're getting started, the first thing you want to do is go to your NuGet repo and then grab the Microsoft.ml NuGet package. For these set of demos, we're using the 0.6 preview version because we want to show you some of the latest features. All the machine learning code for ML.NET lives in the Microsoft.ml namespace here. So if you want to go check that out, you can check that out. So once I've grabbed my NuGet, and I've added my namespaces that I'm going to be using, you're pretty much set to start writing a sentiment analysis, building a sentiment analysis model in ML.NET. The first thing you do here is you start with creating an environment. This environment, think of this environment as a context that you're building for the ML job that we're about to essentially build. For those of you who are familiar with the entity framework, this is very similar to DB context. Now, the next thing we need to do once we've initialized our environment is to figure out how do we read the data set. So the data set that I have here is basically what Gal just talked about. It's the Wikipedia detox data set. And if you take a look at this, it has two columns. It has a sentiment column, which is this column here. And this is a Boolean column. And it's at column index 0. And then there is a sentiment text column, which has all the sentiment text in there. And this is at column index 1. So what I can do here is that I could use the text loader create reader API and and load my data set here. Once I've created my reader, I can then go ahead and start reading in my training data. And while I'm at it, I'm actually also going to go ahead and read in my test data. So I'm going to use my training data to train my model, and I'm going to use my test data to be able to build and to be able to evaluate how well this model is performing. So at this point, we've created our environment, and we've been able to read our data set. And we've been able to read the training data set and the test data set. The next thing I want to do is I want to go ahead and create an estimator, because as Gal talked about, estimator is the thing I need to be able to create a model. So we're going to build this estimator in a stepwise manner. In the first step, what I'm going to do here is I'm going to go ahead and featureize my text. This is what Gal referred to in his slide when he said that we need to featureize our text for us to be able to provide this text to the ML learner that we're going to use next. So right there, with that featureize text method call, I've actually featureized my text, and I'm storing that in a text column. The next step now that I have to go through once I have featureized my text is, as I mentioned, to go ahead and add my learner. So I'm going to carry over the row.label column because I will need it later. And I will create a prediction column where I will store the result of calling the trainer or the machine learning algorithm, which in this case is SDCA classifier. The SDCA classifier, as you can tell from IntelliSense, takes in the label and the feature vector. So it takes two things. So first you come in with data, you transform your data, so you featureize your data. You have a feature vector and you have a label, and then you want to give the label and the feature vector into the learner here. So I'm going to go ahead and do that now. So one of the advantages of this API is that as I'm typing, you can probably see that it's giving me some hints, and like autocomplete is trying to help me figure out what goes in where. The last thing I want to be able to do here is that if I hover over prediction here, what this, when you run this trainer, what this really returns is three things. It returns a predicted label, which is the Boolean value where the sentiment prediction is going to be stored, whether it's true or false, and then it returns a probability and score. For this example, we just need the predicted label. So in the last step here, I'm just going to go ahead and extract that predicted label. I'm still going to carry over my label. I'm also going to carry over my prediction here. And then in the last step here, I'm going to go ahead and try to grab my predicted label. And again, the predicted label is where the result of the sentiment prediction goes in, the Boolean value. So at this point, I have now created the estimator as well. The next thing I have to do is I can go ahead now and build and train my model. To build and train my model, what I need to do is I need to use the estimator and call the fit method on it, which takes in as input the data that I want to train this model with. So as I mentioned earlier, I want to train this with my training data, so I'm going to go ahead and do that. And when this piece of code runs, it's going to return back a model now, which is being trained on the trained data, essentially. Now that I've built my model, the last thing to do here is to evaluate how well this model is performing. So let me just do that as well. So to evaluate the model, what I'm going to do is I'm going to use the transform API on the model here, and I'm going to pass it now the test data. So what is test data? So again, we're training the model on the trained data, and we're evaluating the model on a different data set, which is the test data. And while I'm at it, the last thing I'm going to do here is I'm going to go ahead and add some. We're going to collect some model stats here on understanding how well this model is performing. So let me just do that as well. All right, so that's pretty much it. So at this point, let me just do a recap here very quickly. First thing, when I want to be able to build a sentiment analysis model with ML.NET is you go ahead and you create your environment. The next thing you do is you want to figure out how you're going to read in your data. So you essentially use the Creator API to be able to provide the schema for your data set. You go ahead then and read the train and test data set. You go ahead and create the estimator, where in the first step you featureize your text, you apply your learner, and the last step you actually extract the predicted label field, which has the actual result. You then use the estimator.fit method to build and train your model, and then you essentially just evaluate it using your test data. Does that make sense? Cool. I'm seeing a few nods here. Good. So let me just go and run this and show you how this looks like in the debugger very quickly. So in reality, when you're building machine learning models, you use a lot of data. In this case, I'm using a very small data set. So this process is going to be fairly quick. But if you're doing this in reality, this training a model and building a model takes a lot of time. So as you can see, the breakpoint that I set gets hit. I'm just going to step over here, and I'm going to go under this metrics column here. And once I drop down the metrics file here, you'll see a bunch of model stat metrics here. So since this is a binary classification task, some of the metrics are accuracy or area under the curve. you can see the accuracy of this model that I just built is about 0.78, which is not bad given the training data set was very, very small. The range for the accuracy is from 0 to 1, essentially. So the last thing I want to do is, Gal also covered another concept there, which is called prediction function. So what I'm going to go ahead and do is I'm going to show you how you can also create a prediction function. And the prediction function is useful because you can then use a prediction function to be able to provide it just one sentiment data and then get the output of that sentiment or get the prediction for that. So I'm just going to go ahead and do that. The prediction function takes in these two classes. These are the input class and the output class that I've defined below. And it also takes in the environment, which we created earlier. And now I'm pretty much there to get my result prediction here. So I can go ahead and say pdf.predict, and I can pass in it a new sentiment issue, where let's say the text is, this is a very rude movie. So this is a sentiment that I'm passing in. And since the sentiment analysis model is essentially telling whether the sentiment is toxic or not, this should come back as toxic. So again, I'm just going to set a breakpoint here and run this again. And again, this should be really quick because I'm using a very small data set. Loading. All right, so as you can see, the breakpoint again gets hit, and if I go under result prediction, you will see the predicted label field, which is now saying true. So what I've just done here is I've shown you pretty much the high-level concepts that you'll be using as you're using ML.NET. And hopefully this makes sense to you, and Gal next is going to show you some of the more other examples of how you can build some other models with ML.NET. Thank you.
Great. So let's now go back to that GitHub example that we talked about a bit earlier. So this is an example of an issue on GitHub. And what we're going to do is take the title and the description of the issue as the features. This is the input to our model. It is what an engineering lead would look at when they're trying to decide what is the area for this issue. The label is area-system.io, the thing that we're trying to predict. Again, this is a classification issue, this time with more than 2 labels. So it's all the different classes of the areas where an issue might belong. All right, so let's switch over to the demo. So similarly, we have Microsoft.ml here. We have a couple of data sets. In this case, the issues train data set is a collection of all the issues taken from the CoreFX GitHub repository, where we have the area, the title, and the description for these issues. Now, I'm not going to write all of the code for this, but I want to go over the key concepts again just to kind of help understand them. So you can see that we start by creating the console environment, and we're creating this multi-class classification context that we will use. We then load our data by telling it what are the columns that we actually care about in this data set, and how do we want to read them in. So we want area from column index 1, which is text, title and description from column indices 2 and 3, and that's all we need. I define this loss function, which we'll use a bit later, and now I want to actually write the estimator. So let's look at what that, or let's see what that looks like. So we start with the reader, and we say make new estimator. Then the first step is actually to just convert the area, which is currently a string, to a number. Remember, we want everything to be numbers for the learning algorithm. So what we're going to do is create a new column called label, and we're going to take row.area and tell it to key. This will convert it to something that can then be used for learning that label. Now I want to take the text as well and featureize it in the same way that we saw in the previous demo. So title, featureize text, and the same thing for description. And again, you can see how IntelliSense is helping me understand what is available at each step based on what are the columns and what are their types and what I can do with them. The next step is to normalize the data and combine all of the features that we have into one vector. So first thing, I'm going to keep the label. I'm going to propagate it down this pipeline. And then I'm going to create a new column, features, by taking the title and concatenating it with a description. Because we're using a linear model, SDCA, I want to normalize my data. Now, this is just a processing step that helps us get better results. And one thing that you can imagine is that as we build out these APIs, we enable analyzers that help you identify when this normalize might be needed. We could later add a warning or an error that says you should consider adding a normalizer to get better results. Now I keep the label again, but I want to actually train the model. So I create a new column, score, and I use my context again that I created earlier to look at what trainers are available to me. In this case, I just have SDCA again. I give it the label. I give it the features. And I also give it the loss function that we created earlier. Now I want to actually extract, in the same way that Ankit showed, the predicted label from this score. So we can actually hover over this and see towards the right that we have this predicted label string over here. That's the thing that I want to take out of there as a separate column so we can actually get that prediction. So what I will do is, again, keep the label. I'll keep the score. But I'll also create a column, predicted label, that takes the scores predicted label. Now, you can see that the type here is key. So that's what we did over here earlier when we converted that to a key. Now, the thing that we want to get out of this model is not just some number, but actually the string that corresponds to that GitHub issue that we saw earlier. So I can now convert this back to a value over here. And now we're done. So the rest of this is very similar to what we saw earlier. We use the reader to bring in the data set. Now, remember, this is lazy. We don't actually read in the data until we need to. And that's in the estimator.fit step, where it actually takes that pipeline that we created, the estimator, and the data, learns on it, and produces this model. I can now do the same evaluation that Ankit showed and evaluate what the accuracy here is. Now, this is a bigger data set, so we're not actually going to run it right now. But the next step is that I can save that model as a zip file and use it later, bringing it into a different app. And using that model, I can again make that prediction function that takes in the input and output classes for the GitHub issue, give it the title and the description, and get out a predicted label. So what I want to actually show is that if we remove all of this code that trains the model, saves the model, evaluates the model, and just have the model.zip, we can actually still make the prediction. So you can see over here, I have model.zip that was trained earlier. And if I run this, now this belongs in, I think it's it's in link, this particular issue. So let's just quickly run it. And because we're not training, just loading the model and using it for a prediction, this should be relatively fast. So we got area-system.link. So one thing that's worth noting is that we just went through this process really quickly, took the data, trained the model, we're very happy with it, maybe we deploy it. But in reality, machine learning is an iterative process. After we've trained the model the first time, we're probably not going to be too happy with the accuracy, or we want to change some things to make it actually better. So a few ways that we could do this for this particular problem. One is getting more or different data. So in this case, we could consider getting a larger data set. Maybe over time, there are more and more issues in this repository that are labeled, and we can use that additional data to get better results. A rule of thumb in machine learning is that the more data you have, the better results you might be able to get. We might look at the user profiles, so which user actually submitted the issue. Right now, we're looking just at the text that they put. But if we know who they are, and we know that they have worked with particular areas of the code in the past, that might give us a hint on which area that issue belongs to. We might also look at other .NET repositories if they follow a similar issue structure and use that information in our model as well. Alternatively, we can actually try and modify the pipeline and model that we just trained. So I used SDCA, which is a linear learner. Maybe I can try other trainers and other algorithms that are available. And you'll see in IntelliSense that when I click the dot, I can actually see the other learners that are there. Right now, we're just starting with SDCA. But ML.NET already has a wide variety of other learners. There are different transforms that I can try and different hyperparameters. Now, hyperparameters are just the things that you can tune within these components, within these transforms and learners, to try and get better results. And to some extent, there's knowledge that you acquire over time about what is the right thing to use in a particular situation, but it's also a lot of experimentation and just trying out different things to see what gets you better results. And that's why it's really important to have a good process for evaluation and making sure that when you train a model and evaluate it on some data, you're doing that correctly. So now let's talk about movie recommendations.
Right. Does that make sense so far? Like what we've kind of like showed you here, is there like a burning question, like one burning question that anybody has that anybody wants to ask? Yes, sir.
What does the featureized data actually do? It's turning it into a number, but like how is that useful? What's the context?
That's right. Gal, do you want to?
Yeah, so the approach that we're following here is called n-gram. So if you take the sentence that you have over there, we're basically saying, what are the words in it, right? So you can imagine we're creating a dictionary that has, does it have the word rude in it? Does it have the word thank and the word you? So it's separate words, but it's also sequences of words. So thank you, or other kind of two-word combinations. And for each of these comments, we have this vector that you can imagine as starting with 0 or 1 if it has that word or phrase. And then we're doing a bit more on that because some words are really common, so you don't really care about them too much, and others might have more significance, so you weigh them differently. But essentially, we're just kind of mapping the information of what words, what phrases, what characters are in this in a numeric format.
So is that custom written for this one, or that's a feature of ML.NET?
So in terms of the concepts, right, the transformer takes text and gives you the featureized text. The estimator that we have is what trains that featureizer, that transformer, to be able to take text and give out those numbers. So yeah, to answer the question, I guess, yes, we train the model on that data to understand what are the words within it. We can go into that in more detail maybe a bit later.
Does that make sense? Does that answer your question, sir? Yes. Yeah, and in general, like, we're still kind of like designing these APIs, and we're developing this in the open. So, if you want to try this out and give us your feedback through our GitHub issues on the machine learning repo, we'll be happy to take that into account. And also something else that we're doing as a part of these APIs is that we're adding really smart defaults. So so you can take a look at a sample and you're like, okay, the sample is doing sentiment analysis. I want to be able to do sentiment analysis for my app, so you'll be able to use that. And longer term, we're also making tooling in Visual Studio that will auto-generate some of this stuff for you. But we want to give you the basics of ML.NET, so as developers, you are able to understand how these models are being built and so on. So the next scenario that we want to show you here is about movie recommendations. I'm sure like everybody knows what movie recommendations is and has used Netflix and other apps like that. So let's go over a couple of approaches for how you would build a movie recommender, right? So the first approach, which is perhaps the easiest approach as well, is to use something called population averages, right? So what population averages tells us is that I have a particular movie. So in this case, let's say I have The Princess Bride. And I look at this rating, like how other users have rated this movie. And I come up with a particular threshold. And if the rating is higher than that particular threshold that I've defined, then I say that this is a good movie to recommend. So let's say that that's the example that I'm taking, right? So that's like the first approach that you can take. You take a look at the average rating for a product, and if it's higher than, or average rating for a movie, and if it's higher than a particular threshold, you recommend it. Now, as you can imagine that this approach would work in a number of cases. The one drawback that this approach has is that what happens if the user in this case, for example, doesn't like romantic or fantasy movies like like Princess Diaries, essentially. What happens then? So your approach here starts to fail there. Another approach that you could take as you're building a movie recommender is you could use content-based filtering. And by content-based filtering, what we mean here is that you take into account user preferences. So for example, let's say you have a user who likes watching superhero movies, and this user has seen Iron Man or has seen Avengers and likes these movies. So what we do here is we go ahead and recommend them the same genre of movies here. And this approach is essentially content-based filtering. So again, this approach would work fairly well for a number of use cases. But again, what happens if the recommended movie of that particular genre is not a very good movie by itself? So in that case, again, this approach also has some drawbacks there. The third approach that we're going to be showing you with ML.NET is called collaborative filtering. And collaborative filtering is essentially one of the more popular recommender systems that are now being used in a lot of the recommendation systems across the products you use, like Amazon, Netflix, and all that kind of stuff. So let's get into that. So the way collaborative filtering works is that there's one concept behind collaborative filtering. What collaborative filtering says is that if person A has the same opinion as person B on a particular issue, it's more than likely that person A will have the same opinion to person B on a different issue than a randomly chosen person. So to take an example, in this table what we're showing you is 3 users. That's Ankit, Gal, and Cesar. And the columns are showing you the movies that these 3 users have seen. And the tick marks here, or the check marks here, are denoting whether they like this movie, and the cross are denoting that they didn't like this movie. So let's say that given this data set, or given this data that we have now, let's say that we want to be able to predict what's the probability of Gal liking the movie Casino Royale. Does anybody want to take a chance there, whether Gal will like Casino Royale or not? Just anyone that want to? Yes, I think I'm seeing a few nods here. How many people think yes, that's going to happen, right? All of pretty much the entire room. Perfect. So we picked a good example then. So essentially, so here's where collaborative filtering comes in. And in ML.NET 0.3, we've added collaborative filtering through the factorization machines learner, and we're going to get into that. But the insight that collaborative filtering brings in here is that if you take a look at this table or this data, Cesar's movie taste here is very similar to Gal's movie taste here. Both of them like Heat, both of them like Mission Impossible, they both don't like Home Alone, and so on. So based on collaborative filtering, we can use Cesar's data that Cesar likes Casino Royale to infer that Gal has a higher probability of liking Casino Royale as well. So that's basically what collaborative filtering is. So now that we've nailed down the approach that we're going to use the collaborative filtering approach for recommendation. Where do we find this data? We need a lot of data for machine learning, and where do we find data for this particular problem? As it turns out, there is the Movie Lens data set, which is a very good data set for movie recommendation. It has 20 million ratings. It has 27,000 movies across 138K users, and you can go and take a look at that data set if you want. And this data set really has 2 things. It has the ratings.csv, which has the user ID, movie ID, and rating. And then it has movies.csv, which has the movie ID and title. Now, as we did in the earlier examples, let's figure out what features are we going to use to be able to predict whether a person is going to like this movie or not. So the 2 features that we're going to use as we're building our model is user ID and movie ID, and that's pretty much it. And then what we're going to try to predict, or the label, is the rating. If the rating of the movie we predict is 1, then we recommend that movie. If the rating of that movie is 0, then we don't recommend that movie. Does that make sense? Okay. So again, once we've created the feature vector and we've figured out our label, we will go ahead and build and train a model with that. Once we've created the model, we'll build a prediction function, which is a convenience API on top of that model. We'll input into it the features, so the movie ID and the user ID. And what that will return is whether the user liked this movie or not, and then a score for this prediction. the higher the score for the prediction, it tells us there's a higher likelihood of this user liking the movie. So 1 is a Boolean value that, yes, you like this movie. The second is the score, which is the higher the score, the higher that upward for liking that movie is, essentially. So let me go over and switch over to my machine here. And just show you the app here, right? So the app we've built here is a standard ASP.NET MVC app. It's just going to take a minute to just launch. So that's the app, right? So it's, you've probably seen Netflix. It's similar. So this has a few less features, though. So as you can see, there's a few profiles here that we've added. So it's me, Gal, Cesar, who's sitting over there. Let's choose Gal's profile and see what happens, right? So when you see Gal's profile, you'll see the movies that Gal's watched, right? So he's seen Heat, he's seen Terminator 2, he's seen Mission Impossible, he's seen Independence Day. And then the thumbs up here indicates whether Gal liked this movie or not. And then the thumbs down here means that Gal did not like this movie. Really? You didn't like Home Alone? And then the second lane here, that we're showing you a list of movies that are like, all-time box office hits. So it's like, Face Off, Titanic, Casino Royale, and so on. So let me go ahead and click this recommend button, right? And what this recommend button is going to do is that it's going to, like in the app, what's happening here is that this is calling into the ML.NET recommendation model. And the model for each of these movies is coming back with a score between 0 to 100 on how likely is it for the user to like this movie or not. So if you take a look at the movies that Gal ended up liking, he liked Heat, he liked Terminator 2, he liked Mission Impossible, he liked Independence Day, a lot of the action movies. And then Casino Royale and Gladiator here are rated fairly high. It's close to 80 and 90% here. So you can see like how this recommendation is sort of working already. So let me show you something else here now. Let's switch profiles here, and let's go to Cesar's profile. So if you remember from the slide, both Cesar and Gal have very similar taste in movies. So as it turns out, Cesar has also seen Heat and liked it. Cesar has also seen Mission Impossible and liked it. Cesar has also liked Independence Day. Next, let's go ahead and click recommend for Cesar and see what his recommendation scores are for these movies, right? So you'll see here again that Cesar's recommendations here are scores that are fairly similar to what Gal had. Cesar is also like Casino Royale. Cesar is also like Casino Royale. He's also liked, he's probably also going to like Gladiator a lot based on these scores here. Now, there's one glitch in this slide here. Can anybody pick that up? There's one problem. Yes, sir. Perfect. We've already read in Casino Royale, exactly. So we're kind of like cheating here a little bit, and we'll tell you why we're cheating here. So we've read in Casino Royale as a data set, and we've used that data that Cesar's like Casino Royale to build Cesar's recommendation model. So yes, he's definitely going to like Casino Royale because we already know that fact. But what we're trying to show you here is how collaborative filtering is really helping in Gal's prediction. So what's happening in this case is that Cesar, because he has a very similar taste in movies like Gal, they both belong to the same cohort of users. And since Cesar has already seen Casino Royale and liked it, if I go back to the profile very quickly, Gal's essentially going to like that as well, right? So that's really what collaborative filtering is all about. And with ML.NET, we have support for that. Just to complete the pie here very quickly, this is me. I didn't like any of the action movies, apparently. I did like Home Alone, though, so I just want to call that out. And then what you're going to see here is that when I go and hit my recommended scores, I get recommended scores for my movies. All the action movies are fairly low. Some of the other movies are much higher. So let me just switch very quickly to Visual Studio here and show you how we build this model. So I have two projects here. I have the ASP.NET app, and I have the movie recommender application here. And so let me show you how we built the model here, right? So this should be getting familiar to you by now. You start with creating your environment. You then figure out how to read your data. So you specify the schema. So in this data set, if you remember, I said you're going to use user ID and movie ID as the features. And then label is the rating prediction. You read your train and test data. You then build your estimator. And what's really happening in this estimator is step one, you're taking your categorical data and you're applying a transform called one-hot-code encoding. You're then taking the two feature vectors you created. So you created two feature vectors, user ID and movie ID. You want to combine them into one feature vector. Now that you have one label column and one feature column, you want to go ahead and add the field-aware factorization machine learner here. This is what we've added in ML.NET 0.3, and this is what does collaborative filtering. And then I want to go ahead and just extract away the prediction label and the score. So in this case, we're going to not only get the predicted label, which is going to tell us that whether this user is going to like this movie or not. We also want to get the score, which will help us give a percentage on what's the likelihood between 0 to 100 on a particular user liking this movie or not. The last thing to do there is then to call estimator.fit, which will train the model. And then once we're happy with the model performance, we can essentially save it to disk. So one of the advantages of using ML.NET is that once you've loaded your model to disk, it's really up to you. How do you want to use that? You could take that model and make it app local or check that into your ASP.NET app, as we've done here. Or you could put that behind a web API, but it's really up to you. The one last thing I want to show you here before Gal's going to show you some of the other demos here is that the way I'm absorbing this model is in my recommend method here. So I come in, again, I create the local environment. I essentially load my model. Once I have loaded my model, I go ahead and create the prediction function. And then very quickly here, I go over all the movies that you're seeing here. And one by one, I call on the prediction function, the predict method, where I provide the user ID and the movie ID. And that returns to me the prediction that you're seeing here, essentially. So hopefully that makes sense to you. All these samples we're showing you here, these will be in our repo. So you can just go there and take a look at them. So we'll move over to the next example here. But hopefully this makes sense to you. Gil.
You have one more.
Right. And just last thing, I already mentioned this here. So field-aware fact-resident machines, that's the technical term for this learner. And it's used in a lot of scenarios like click-ad prediction and so on. So you can take a look at that. Gal's going to get into deep learning now, which is another facet of machine learning. So Gal.
Thank you. So you might have heard of deep learning. Deep learning is an area of machine learning that's been revolutionizing areas like computer vision and speech recognition. Today, if you wanted to go and do that example of taking an image and detecting a face or a dog in the image, you're probably going to involve deep learning to some extent. Now, the concepts behind deep learning, like neural networks, have been around for many years. But they've only become really powerful and popular in the last decade or so because of the amount of data and compute power that is now available. Now, Ankit talked earlier about ML.NET being a framework. So we're integrating TensorFlow and Onyx to be able to use them and score models from them in ML.NET. And I'll go into what that means, starting with TensorFlow. So TensorFlow is a really popular deep learning library that allows you to create, train, evaluate, and consume deep learning models. We're going to use a pre-trained model from TensorFlow. So that means someone else created this model in TensorFlow and uploaded it to the internet or made it available to us to use. The name of this model is Inception. It takes an image and tells you which of 1,000 classes is in that image. So it's cats, dogs, cars, and so on. Now, this is implemented as a transformer in ML.NET. So it's something that takes data, does some work on it, and outputs new data. In this case, the input is an image, and it outputs the scores for each of the classes. So let's do a few quick demos. So this should look familiar by now. We start by downloading the model from this location. We bring in the Microsoft.ml NuGet packages, as well as the image analytics from Microsoft.ml and Microsoft.ml.TensorFlow. I have a couple of images here. For example, an image of my dog. And I've also downloaded this inception model earlier. So when you download that model, you get this .pb file, which represents the model and the model weights. But you also get this inception labels file that tells you what are the classes that this model detects. And it maps an index to each thing that it detects. So it could be a Siberian husky, a gray whale, and so on. Now in my app, I'm not going to actually train a model. I'm just going to take that TensorFlow model and use it to make a prediction. But all of this looks very similar. We start by loading the data. We create that reader. And we bring in the image path of the image. I create the estimator, running a few transformations on the data. I load the image. I resize it. And I extract the pixel values from it. I then apply the TensorFlow graph to it, giving it the model location. Just as before, we make the prediction function. And now we can actually just provide it the image path of my dog and get a prediction. Now it's going to give us the scores for each of those separate classes. And we're going to just identify what is the maximum score and which thing does it correspond to. So if I run this, again, we're not training a new model. We're just taking that TensorFlow transform and using it to make a prediction. And in this case, the predicted label is Lakeland Terrier. So let's do another example. I'll switch quickly. So next example is style transfer. So you might have seen these types of demos before, where you're taking an image and then applying the style from another image to it. There's actually a website that you can visit right now, styletransfers.azurewebsites.net, to try this out with your own camera or bringing in other images. What we're going to do is actually take the code that happens behind this website and rebuild it with ml.net. So what we have here is a really simple app, and we're looking at the method that takes in the image as a byte array, applies that TensorFlow transform again, this time with a different model, outputs the image, and then just displays it. So let's see what that looks like. So now you can see me. And what we're going to do is select the mosaic style over here. And then it's going to pass that image through this model into a different style. So it takes the style from a different image and applies it over here. And this is a pre-trained model. So we actually just downloaded, we trained this model elsewhere using TensorFlow, and then applied it to this image. And what it's doing is it's trying to kind of create a new image that has the same content as the image that I have over here, but applying the style from another image. So let's try a different one really quickly, candy. And now I look like candy, apparently. But you can try this out. So there are a few other styles available here as well. So this is one kind of neat demo to show how you can use deep learning models to kind of apply styles from a different image.
Right, and I think like when you're using image classification, like if you have that scenario, like you were essentially going to use deep learning based models there. So that's just just a hint there.
All right. So the other approach to deep learning that I mentioned is Onyx. Has anyone here heard of Onyx? Okay. All right. So Onyx is an open model format that allows developers and data scientists to use whatever tool they want for machine learning. So all of the ones that you see on this image. And then you can convert the model that you get from those tools into this intermediate model format, Onyx. From there, you can actually maybe convert back to a different tool or just deploy in many different apps, taking advantage of hardware acceleration and just having confidence that that model can run within that location or that application. So there are many Onyx models available on the internet today, and we took one for emotion detection. So So this will look very similar to the code that we had for TensorFlow, where I have a couple of images here with emotions. They're really small, 48 by 48, but you can okay, it's not zooming in. Oh, there we go. So you can see this one is a happy photo. Now, I have the same thing over here, where I have the reader. I have the model in a particular location. It's a .onyx file. I apply similar transformations. This time, I add the as grayscale transformation, and then apply Onyx model, giving it the model location. I create my prediction function, and then I can run it. So one thing to add while this is running, the TensorFlow transform was already added in ML.NET 0.5, and the Onyx will be coming soon to ML.NET. Now we can see here the predicted emotion is happiness. So in this case, it was correct. I didn't have to train the model. I didn't have to label any of this data because I downloaded a model that already works for this, and I was able to start predicting on these images that I have over here. Just to recap, we're starting to integrate deep learning into ML.NET. We're starting with just being able to take models that you've trained somewhere else and scoring them, getting the scores from them in ML.NET. But in the future, you can imagine that we'll enable training some new models and better integrating with these frameworks.
Right.
I'll hand over to Ankit.
Thank you. Yeah. So hopefully that makes some sense, and we've shown you a number of scenarios here today that are possible in ML.NET. So, if you haven't already, check out our repo. You can go there and see some of the other scenarios that we didn't have time for demoing, but that's definitely there. The one last thing I want to mention here is that we launched ML.NET 0.1 at Build this year. It's been 6 months, and since then we've been releasing every month. It's usually the first Tuesday, I believe, of every month that we release, unless it's a holiday. And as a part of these releases, we've been adding some real goodness in the open, right? So in ML.NET 0.2, we added the clustering machine learning tasks if you want to do clustering, which you can do if you want to do customer segmentation. We added that. ML.NET 0.3, we added support for recommendation. We showed you that as a part of the movies demo. In ML.NET 0.4, we made F# a first-class citizen in ML.NET by fixing some of the issues that we had in our APIs. We added new learners, new transforms. Some of these learners and transforms, for those of you who are familiar with Kaggle, are the ones that win all the Kaggle competitions. And now in ML.NET 0.5, we've started to add deep learning into ML.NET, as Gal mentioned. The API is something we're still building. Like what we just demoed here throughout the talk here is essentially the new API that we're building. We're looking for feedback on that API. But as you can see, we've already come a long way since build, and we've added a lot of stuff here. We're seeing a lot of good engagement from the community here as well, and we're going to keep working on this. As a part of the roadmap for ML.NET, and what you're going to see there is things like, we're going to improve the API, make it more developer friendly. We're going to add additional ML tasks. So, for example, if you want to do time series or anomaly detection, we're going to add that in the ML.NET story. We're going to improve the deep learning support with TensorFlow. We'll add ability to be able to scale out your model training into Azure so that you can actually do it a lot faster. Some of the code that we showed you today might seem complex, especially for model training. So we're also building a UI that will allow you to auto-generate the model training code. We're improving the tooling of Visual Studio for improving the debugging experience, IntelliSense, and so on. And lastly, we're also innovating C# as a language to be able to add new features to C#, to be able to do some of these machine learning tasks fairly easily. But that's currently the roadmap that we have for what's next with ML.NET in the months to come. So hopefully that makes sense. The one call to action before we get into questions that we want for you folks to walk out with is that if you want to get started with ML.NET, you can go to our website, which is .NET/ML. There you're going to find a page there where you can go, and it gives you a very good getting started tutorial on how you can build your first app with ML.NET. You can try our samples, as I've mentioned a few times. You can take a look at our docs. And for those of you who really want to get involved with the ML.NET project, you can check out our ML.NET repo and pick up some of the tasks. You can contribute to the repo. You can provide feedback on the APIs and really get involved here as we're building this in the open. So that's all we kind of like had to show you today. We're happy to take any questions that you have in the last 10 minutes here. There's a mic up front, so if you want to come and perhaps ask us any questions. We will also be around outside for you to ask any questions if you want. But thank you so much for coming here today. Thank you for your time.
Thank you.